So in this lecture, we're going to continue from the flipped class video and continue studying the dot and the cross product. So let's just recall quickly what the dot product was from the flipped class video. So if we're given v to be, say, x1i plus x2, or let's say y1j plus z1k, and say w is x2i plus y2j plus z2k, then the dot product between these two vectors is we just multiply the coefficients. So it's x1, x2 plus y1, y2 plus z1, z2. And we're going to see lots of ways this is an interesting construction and how it tells us stuff. But one of the things we did see is this gives us we can use this to measure the magnitude of a vector. So we saw in the flipped class video that if I take v and I dot it with itself, well, this is x1 squared plus y1 squared plus z1 squared, and this is exactly the magnitude of v squared. So this dot product gives us a way to measure the magnitude of a vector, which is quite useful, and we'll see that come up quite often. Let's go ahead and look at some other properties that the dot product gives us, though. So think of our vectors v and w. So let's say we have v here, and say this is w here. So given two vectors, even if they're three-dimensional vectors, they lie in a plane. Let's draw a plane here that these are in. And we can look at the angle between these two vectors here, so theta. So it's going to be the acute angle, so we'll let theta be the acute angle. So not the bigger one, the one that's less than or equal to 180 degrees. And this angle is in this plane that they're both in. And so we can ask, can we tell what this angle is? So what is this angle? And we can actually use the dot product to tell us this. So we're going to have a formula which we'll show below that says if I take the dot product of v and w, I get the magnitude of v times the magnitude of w times cosine of this angle. So let's go ahead and see how we do this. We're going to use the law of cosines to do this, which I don't expect you to remember, but hopefully you've seen it at some point in the past. So let's take our vectors here. And so we have our vector v and our vector w. We have this angle theta here. And then recall that this vector that goes from here to here, this is v minus w. So you can think of it, if I take w, I put v minus w on the tip of it, I add those together. Those w should cancel and I should get v. So now, if I forget about the vector part of this for a minute and think of these just in terms of a triangle, the side of the triangle here is the magnitude of v. The side of the triangle here is the magnitude of w. And the side of the triangle here is the magnitude of v minus w. So now, if we recall the law of cosines, like I said, I don't really expect you to remember this, but this would be the side opposite of theta of the triangle squared is equal to v squared plus w squared minus 2v w cosine theta. So you can almost think of this as a correction on the Pythagorean theorem, because if we had a right angle here, we wouldn't have this extra term with the cosine, we'd just have the Pythagorean theorem there. So it's a correction on that, taking into account that the angle is not 90 degrees. So if this was 90-degree angle, then the cosine would be 0 and that would go away, and we would just recover the Pythagorean theorem. So let's just look at this side here for now, and let's look at that in terms of the dot product. So I know that the magnitude of v minus w squared is the same thing as v minus w dotted with v minus w. That was our result above. So So remember up here we had the vector dotted with itself is the magnitude squared, so we're just using that in the other direction. So let's go ahead and distribute this out. So this is going to be v dot v minus v dot w minus w dot v plus w dot w. And now we can rewrite these. V dot v we know is magnitude of v squared. The w dot w is magnitude of w squared. And then remember, the order of the dot products doesn't matter, so I can rewrite this as 2v dot w. So now let's plug that into the equation above. So we replace the left-hand side with what we found. So I have magnitude of v squared plus magnitude of w squared minus 2v dot w. So that's the left-hand side, so that's what we're replacing into here. And then the other side we had was v squared plus w squared minus 2v w cosine theta. And now just notice here, we can do some cancellation. So this cancels with this cancels with this, and then I can also cancel the negative 2 from both sides. And once I've done all that cancellation, what I'm left with is exactly what we were trying to show. V dot w is magnitude of v, magnitude of w, cosine theta. So not too hard to show if you remember the law of cosines. Of course, if you don't, then it's quite difficult, but now we have it so we can use it. So this is really important formula for several reasons. So let's start off with a definition. So we say vectors v and w are orthogonal or perpendicular. Either language is fine, so you need to be comfortable when someone uses either orthogonal or perpendicular if the angle between them is pi over 2. Right, so this is exactly what you would expect to think of for two vectors being orthogonal. If I have v here, or perpendicular, and I have w here, well, we'd want this to be a 90-degree angle for them to be perpendicular. And orthogonal is just a new word we're introducing for perpendicular. But now let's think about what this says above. If the angle between v and w is pi over 2, look at our formula up here. So what would that mean? So if theta is equal to pi over 2, well, when I look at v dot w, I know this is the magnitude of v, the magnitude of w, cosine theta. So as long as v and w are not the zero vector, this is the same thing as saying, well, cosine of pi over 2, so let's maybe just replace the theta there with our pi over 2, well, that's 0. So this is 0. And the only way the right-hand side there can be 0 is if the angle is pi over 2. So we actually get, and this is a very important fact, v and w are orthogonal, which I'll also write like this sometimes, if and only if v dot w is equal to 0. So remember, the dot product is something that's very easy to calculate. So this gives us a very fast way to calculate if two vectors are orthogonal. This is going to be super useful for us in lots of situations going forward. So let's go ahead and look at an example using what we've done so far. So let's find the angle between the pairs of vectors. So for the first one, let's do v being I minus 3j minus k, and w being I plus j plus 2k. So there's a few things we need to calculate here. So if we look at our formula above, I need to know v dot w, I need to know the magnitude of v and the magnitude of w. So we're going to calculate all those things to start with. So v dot w, I have 1, and then I have minus 3, minus 2. This gives me minus 4. Magnitude of v is going to be square root of 1 squared plus 3 squared plus 1 squared. So this is square root of 11. Magnitude of w is square root of 1 squared plus 1 squared plus 2 squared. So this is square root of 6. So my formula reads minus 4 is equal to square root 11 square root of 6 cosine theta. So then theta is arc cosine of minus 4 over square root of 66, which is about 1.63 radians, or about 93.47. So that shows us 90 degrees. So that gives us the angle between these two vectors. So let's try another example. So let's say v is I minus 3j minus k, and u is minus 2i minus j plus k. So same v, we've just changed our u here. So v dot u in this case is minus 2, and then plus 3 and minus 1. So this is 0. So this tells us that these vectors are actually, so v is actually perpendicular to u. So that's a nice use of dot product to be able to tell us angles between vectors, and in particular when they're perpendicular. There's another super important application of dot products, and that's breaking vectors into components. Okay, so for example, if we're thinking of a force pushing a vector or pushing an object along a displacement, so if F moves an object a displacement of vector d, the only part of the force that contributes to the work is the part that's in the same direction as d. So if you're thinking of this in terms of a picture, so maybe I have some displacement vector here, d, and I have some force vector, F, like this. And so what this is saying is that if I look at this vector here, the only part of it that's actually doing any difference or any work is the part that's in the same direction as d. So I can break this vector up into two pieces here. The part that's in the same direction as d, and the part that's perpendicular to d. So if you think of this in terms of a real life scenario, think of if you're pushing a desk across the room. If you push straight down on the desk, it's not going to go anywhere. It's only the force that you're pushing horizontal, so the part that's parallel to the floor, that's actually moving the desk. So that means what we would like to do is we'd like to know, what is this component, this pink component here? So what is this? So the way we'll write this is the projection of F onto D. So that's this vector, and we want to calculate this. So let's think about how we can do this. So this is the projection. We'll say this part here, this is the perpendicular. So we'll say perp of DF. And let's say this angle here is theta between these two. So this here is, of course, a 90-degree angle. Okay. So what is the direction of the projection? Well, if I want just a direction vector, this should be the vector in the same direction as D, but I want it to be a unit vector. So let's take it to be that. And now if I'm thinking of this in terms of a triangle, this is theta, this would be the magnitude of F, and so this side here would be magnitude of F cosine theta. So that should be the magnitude of the projection vector. So our projection vector then, of course, is just the direction times the magnitude. So we just figured out what that is. This is the magnitude of F cosine theta, and then the direction is the direction of our displacement vector. Now this isn't the best way to calculate it because you'd have to go through and actually calculate the angle here. But what we can use is, let's recall that if I take F dot with the displacement vector, this is the magnitude of F, the magnitude of D, cosine theta. So we have almost the dot product there in the top. So notice if I have this part here, I have everything except for the D there. So let's go ahead and just add that in. So if I put magnitude, and of course I can't just throw vectors in, so let's put it in the denominator as well, so we haven't changed anything. But now I can rewrite this as the top part is F dot with the displacement vector, and then if I gather the bottom, I'd have magnitude of D squared, the vector D, and I know the magnitude of D is the dot product of D with itself. So to recap, what we've just discovered is if I take the projection of the force vector onto the displacement vector, this is exactly the force dotted with the displacement over the displacement dotted with the displacement. Now this is a scalar, and then D. So that's quite a nice formula, and it's easy to calculate to figure out what is the projection of one vector onto another. And now we can also use this to get the perpendicular vector, because notice the projection plus the perpendicular is the original vector. So we know that F is the projection vector plus the perpendicular vector. And so since we just calculated the projection, we can use that to get the perpendicular. So this is just F minus what we just calculated. Okay, so not so hard. So let's continue on with this idea of work here. So we learn in elementary physics. So what we did above, of course, works for any vectors. We used F and D for forces and displacement, but any vectors work. But in elementary physics, we learn, before we have any idea what vectors are, that the work is the force times the displacement. And these are when we're just talking about scalars, force The force is just a scalar and displacement is just a distance traveled. But let's see, how does this work when we actually have vectors here? So in this case, we saw that the only part of the force that should contribute should be the projection. So our work should really be the magnitude of the projection of F, and then the magnitude of the displacement. That would be what we'd be getting from this elementary physics formula if we were working in terms of vectors. Now let's think about what we have in terms of these terms here. So we know that the projection vector of F onto D, well, this was F cosine theta over the magnitude of D. That's what we originally saw. So if we look at this, if we have the magnitude of the projection of D onto F, this should be the magnitude of this over here but now of course the magnitude of scalars just comes out to be the absolute value since the magnitude is always constant. We just get this. And so this is just the magnitude of d over d is just 1, so this is just f absolute value of cosine theta. So if we say that the angle here is between 0 and pi over 2, so because we want the force to be in the same direction as the displacement, not in the opposite direction, wouldn't make any sense to be moving it then the cosine is positive. So if we combine this back above with our work, remember our work was the magnitude of the projection times the magnitude of the displacement. So substituting this in, I have the magnitude of F cosine theta magnitude of D, which is exactly F dot D. So we see if we think of work in terms of displacement, or in terms of vectors here, the work is the force dotted with the displacement. And this is going to be important for us later, not because this is a physics class, but we're going to use this idea of work to motivate some other things that come up later in the course. So just remember that we worked out that the work was the force dotted with the displacement. So this gives us a lot of good uses for the dot product so far. So we're going to, before we move on to the cross product, a couple of more things. We can do the dot product in as many dimensions as we want. So if we, let's say, v be x1 through xn, and w be, say, y1 through yn, and these are vectors in Rn, then we can define the dot product of these to be just like in 2 or 3 variables. We just extend it to n variables. So it works no matter how many variables we have. We don't have the nice geometric notions when we get higher variables, but it can be quite useful. So let's see an example that's not a physics example to see how we could phrase things in terms of vectors and dot products. Okay, so we have a local taco stand selling its products here at prices P. So we've got tacos, burritos, quesadillas, and sopas at prices P1, P2, P3, and P4. So we can represent this as a vector. So as a price vector. So we'll see our price vector here is P, and this is P1, P2, P3, and P4. And let's say our taco stand sells, say, Q1 tacos, Q2 burritos, Q3 quesadillas, and Q4 sopas. And so we can write this as a quantity vector. Like this. So then we can represent the revenue for the day well, this would just be P dot Q because it's the price of the tacos times the number of tacos sold plus the price of the burritos times the number of burritos sold, and so on. So we see it's often useful to write things in terms of vectors here, even if they're not like physically what you'd think of as something with a magnitude and a direction. We can still represent them as vectors. So we represented here the prices as a vector and the quantities as a vector. And that way we could think of the revenue here as just the dot product of the two. So it does come up that we use things other than things from physics for vectors. Okay, so now let's move on to the cross product. So let's recall from the flip class video. So if we have V is, say, X1, Y1, and Z1, and W is X2, Y2, and Z2, then we define the cross product. Let's go ahead and put it here. Well, we wrote it in terms of this determinant. And this was given by, we cover up the first row in the first column. So we have this determinant then left over. This is times I, and then we switch the sign, cover up the first row in the second column, and we're left with this. And then finally cover up the first row in the third column, and we get this. And then we can go ahead and take these small determinants to work this out. So y1z2 minus y2z1i minus x1z2 minus x2z1j plus x1y2 minus x2y1. Okay. And again, you should not memorize this final formula. You should understand how to get it from the determinant here. So one of the properties we saw in the flip class video was that if I take a vector and I dot it with the cross product, I got 0 in either way. But what we saw above was we saw that that means that the vectors, if you dot them together, they're perpendicular. So we get that V is perpendicular to V cross W, and W is perpendicular to V cross W. So that's pretty important because this is giving us a way to find perpendicular vectors. So if we draw a picture of what's going on here, if I have my vector V here, and I have my vector W, say here, my cross product of these has to be a vector that's perpendicular to both of them. So that looks like something like this. It's perpendicular here and it's perpendicular here. And the way we get the direction is the right-hand rule like we used for our coordinate axes. So think of putting your right hand down the vector v, so your fingers are pointing in the direction of the arrow of v. Curl your fingers to close your hand towards w, and the direction your thumb points is the direction of v cross w. So this is super important construction. It gives us a way to get these perpendicular vectors, which are important for a lot of things. So this will help us, for instance, come up with the equation of a general plane in 3 space, which is what we're going to do next. So let's consider a plane now. So if we think about a plane and what we would need to specify the plane, think about this plane just say floating in space here. Well, I could say if I have a point P, let's call this x0, y0, z0, that kind of fixes where it is in space, but I could have a similar plane in space that also goes through that point. So say that's also P. Right, so you can think you could rotate this plane in all kinds of different directions, and it would still go through that same point. And similarly, I could have a plane, if I know kind of where it's direct, like what it's facing, I could shift it up and down. So what we really need are 2 things. I need to know the direction of it, which I can think of as having a normal vector telling me kind of what direction it's facing. And then I need a point to tell me where it is in space. So let's use that to see how we can come up with an equation for a plane in space. So let's let P, being our x0, y0, z0, be a point on the plane. Now let's let Q be any other point. So let's just call this x, y, z. Just be any other point. All right, so I'd like some kind of equation that restricts what x, y, and z can possibly be. So let's think of having our plane here. And now suppose we have that normal vector like we said we needed, a normal vector to the plane. And then I have my 2 points. Say I've got P here and Q here. So I can form the vector from P to Q, and that stays inside the plane because both points are in the plane. So I have PQ is the vector x minus x0, y minus y0, z minus z0. And so now since n is a vector normal to the plane and PQ is a vector in the plane, we know that those have to be orthogonal to each other, so their dot product has to be 0. So if we say gave n coordinates here, say these are, the normal vector here is ABC, then this equation here describes the plane because it's saying any point on the plane has to satisfy this equation. But we could write that out, and that would become A times x minus x0 plus B y minus y0 plus C z minus z0 equals 0. And this is our equation, general equation for a plane in 3 space. It's determined by a point and a normal vector. So let's go ahead and consider an example and calculate the plane based on some information. So let's find an equation for the plane containing the points. So I'm going to give 3 points. 3 points are enough to determine a plane. So let's say 1, 2, and 3. Q is, say, -1, 2, and 4. And we'll say R is 2, 0, 5. So if we were drawing this plane, just say we have P, Q, and R. Now, we commented above that in order to give an equation of a plane, I need a point on the plane and I need a normal vector to the plane. Well, I certainly have several points on the plane here, so that's not a problem. But what I need is a normal vector. So what I can do is I can form these two vectors here. So I form PQ and PR, and those will both be in the plane. So PQ is going to be the vector -2, 0, 1, and PR is going to be the vector 1, -2, 2. And so those are both vectors in the plane. So if I take the cross product of those, I'll get a vector coming out of the plane that's normal to the plane. So N, my normal vector, is going to be PQ cross PR. So if we do this, this gives me a 2i minus, and I'm going to have -4 minus 1j plus 4k. So this is 2i plus 5j plus 4k. So now from our work above, the plane then, this is given by 2, and then you can pick any of the points to use for this. So we'll go ahead and use the point P here. So I'm going to have x minus 1 plus 5, y minus 2 plus 4, z minus 3 equals 0. And that's the equation of my plane. So we can also remember back when we did tangent planes, and for our tangent plane approximation, so recall that for tangent plane approximation of, say, z is equal to f of xy at p is equal to x0, y0, our tangent plane was given as so I had z is f of x0, y0 plus the partial with respect to x plus the partial with respect to y, like this. So recall that this was just like if I have a surface, what were we doing with this? We have some surface here like this, and we had some point, and we were finding the tangent plane here at this point. And this point here, this was the point P, which is x0, y0, f of x0, y0. So let's make sense of this in terms of what we were doing. So if you recall, when we were coming up with this, we had a tangent vector in the two different directions, and this was, say, f of x, x0, y0, in that direction. So that was kind of giving us our direction. So what was our vector for this? So our vector, one of them was, we just go j hat, so we want to go in the j direction. And then how are we changing? We're changing with the partial derivative in that direction. So maybe this is this vector. And then v2, we want this just to be I plus f of x, x0, y0. Okay, so that tells us how much to change in the vertical direction. And that's what our tangent vectors, that's how we were getting the tangent vectors to tell us what the plane looked like. So what would our normal vector be then? Our normal vector would be v1 cross v2. This would be 0, 1, f of y, and 1, 0, f of x. I'll put the points in at the end, but this will save us a little writing. So this then would be f sub x, x0, y0, I, minus, let's see, so then cover that. So minus f sub y, x0, y0, j, plus, and then I'm going to have a negative 1 k hat. So this normal vector here is f sub x, x0, y0, I, plus f sub y, x0, y0, j, minus k hat. So then what is our equation for this based upon what we've done above? Well, this would be f sub x, x0, y0, x minus x0, plus f sub y, x0, y0, y minus y0, plus negative 1, z minus z0 equals 0. Well, if we bring the z to the other side, this exactly gives me z is equal to z0. And noticing that this is f of x0, y0, this is exactly the equation for the plane that we had when we were doing the tangent plane. So we see we can recover that from our new version of coming up with planes based upon the normal vector and using the cross product here of those two tangent vectors. So there's one more topic for cross product that we will use later on, so it's important to cover now. So that's the formula. We're not going to go through why this is true. It's kind of a giant, messy calculation. You can find it online if you really want to see it. But the magnitude of the cross product is given as the product of the magnitudes times sine theta, where theta is again the angle between them. Okay, so we can just take this formula for granted for this class. But let's see how we're going to use this. So let's suppose I have my vector here, v, and then my vector here, w. And so this angle is theta here. Well, we can consider forming parallelogram here like this, and then notice that if we're thinking of these in terms of side lengths, and drop this down here as well. So this side length here would be w sine theta. And so if I think of just taking that parallelogram and kind of moving the left triangle over to the right, I get a side here that's magnitude of v, and the side here that's magnitude of w sine theta. So what that's telling me then is that this magnitude of v cross w, this gives me the area of the parallelogram spanned by v and w. And we're going to use this later when we're doing integration and we're looking at surface areas. This is going to be important because we're going to approximate surface area with little tangent planes. So if I want surface area like this, and I want some little bit of surface area here, I might not know how to calculate that, but I can find the little tangent plane right here, say, piece of it, and I'll be able to use this formula to find the area of that tangent plane there, which will be super useful for approximating our surface area. And that's how we'll end up coming up with our limits.